Hey guys, it's Miss Hennessy. I am having, trouble with my camera. There we go. A little bit closer up so you guys can see me. Last day in the classroom. I'm in here cleaning up and getting ready to head home. And so I figured while I was here, I'll go ahead and do our chapter 4 review one last time in room 110. And then everything else will have to be from home. But I want to go ahead and look through that chapter 4 review guide. So if you could grab those, I'm just going to hit some high points. I'm going to make sure I talk about things that have been on recent FRQs in the past 5 to 10 years, terms that have come up that are possibilities that we could see again on this upcoming free response question. Remember, we're 2 weeks out, 2 weeks from tomorrow, May 19th, 2 o'clock. That is the AP exam. So I know that, it's a lot of work, but, hang in there. We're going to get through this together and, give me 2 more weeks and then we're out of here. We're done. I know seniors, it's hard to keep working right now with your last official day being this Friday. So hopefully some of your other classes are finished and you can just focus on your AP stuff to get through your exams. So, all right, so let's go ahead and take a look at sensation and perception. So I'm just going to kind of go in order through the review guide with you, and I'm going to try to move as quickly as possible. I know you probably don't want to sit here and watch a hour-long video of me rambling. So starting with sensation perception, just making sure you understand the difference. When we talk sensation, we're talking about those actual sensory receptors. Those sensory receptors exist in our eyes, our ears, our nose, our tongue, and on our skin. And so that's what receives incoming stimuli from our environment. The actual taking in of that stimulus, whether that's light wave, sound wave, chemicals that we smell or taste, taking in that information, transforming it into a neural message that the brain can then start to perceive. This is where perception starts once we get to our cerebral cortex and we start using higher level function to organize and make sense of sensory information. Okay, so with perception, we talked in the beginning of this chapter about bottom up and top down processing. Bottom up, starting with our senses, working our way up to higher brain areas to make sense of the incoming information versus, I feel like this is so not clear there, versus top down, which is where we have that perception already in place. We have an expectation, and then we work through our senses. A good example I ran across recently was when you're doing a puzzle, and maybe being in quarantine, I know a lot of people have been doing puzzles at home. So if you've done a puzzle, think about when you're looking at the box. When you're doing a puzzle and you're looking at that picture on the box, that's top-down processing. You already have that expectation of what that puzzle is going to look like when it's finished, versus if you just had a bunch of puzzle pieces, but you didn't have the picture to look at, or you were, completing a puzzle like upside down, where you weren't sure of what the finished product was going to look like, but you had to use your senses to work your way up to that perception. I also put the flower, I think it's like flowering love or something. I don't know what that rose with the 2 people making out in the middle. I put that picture in there for you. We talked about that one in class. Moving on, so selective attention is a term that has come up on the AP exam. Remember, just that ability for us, or inability, however you want to look at it, to be able to focus on more than one stimuli at once. So we're selectively attending to, maybe your teacher's voice in class, or to our text messages on our phone, or our calculus homework, or whatever. That selective attention is our ability to attend to one stimuli, whether that's something visual or auditory, at a time. So examples of that have also come up on the exam. One is the cocktail party effect. Cocktail party effect has been on FRQs recently. Remember, that's just our ability to be able to attend to one voice among many when we are in a crowd. So in the hallway, during class changes, and we are, at our locker talking to our friend, we can attend to their voice among all of the other voices that are going on around us in the background. Inattentional blindness is another one that has been on an FRQ in recent years, and that is going to be the video we watched of the moonwalking bear, where you were counting the passes of the people throwing the basketball. So instead of, paying attention to the fact that a bear was moonwalking across the middle of the screen, we were counting passes. So because of that selective attention or inattentional blindness, we failed to see something that was right in our visual field. And then change blindness is the Darren Brown video where they were swapping out people and they were asking for direction. Going down to your thresholds, absolute and difference threshold both have been on recent FRQs. Difference threshold has actually come up twice. So I'll start with absolute threshold. That's just the minimum level of stimulation that you can detect at least 50% of the time. So what's the minimum amount of light that your eyes can detect? What's the minimum amount of sound that my ears can detect or taste, etc.? So that is your absolute threshold. Remember, that's at least 50% of the time. As we get older, our absolute threshold is going to increase. So the older you get, the more stimulus it requires for us to be able to detect. It's why your parents don't see as well or hear as well as you do. They require a louder sound or a brighter light to be able to see. Okay? Then difference threshold is that minimum difference that you can detect between two stimuli. So this is going to be, looking at paint samples, being able to detect the difference between two colors, lifting weights, being able to notice the difference in the different, heaviness of a weight. On your handout, you have the lights. So looking at difference threshold with the brightness of these light bulbs. Obviously, it's a picture, but and then Weber's law is what applies to that difference threshold. So Weber's law is what says that in order for us to detect that difference, it has to be a difference that's constant, a constant proportion or a constant percentage, not an amount. Okay, so I gave you an example in class. If we wanted to sweeten a glass of tea or a pitcher of tea, we wouldn't use the same amount of sugar. We would use the same proportion. So as your stimulus size gets larger, you go from just a glass of tea to a whole pitcher, now that difference threshold gets larger. It requires a bigger difference. It requires more sugar to sweeten the pitcher than it did the glass. I hope that makes sense. But difference threshold has come up a couple of times, I think, in contexts like playing an instrument, listening to music, being able to hear the difference in the sound of, chords or different, tones. When like cooking or making food and you're adding spices and being able to detect a difference in taste, those would be examples where it might be applied in an FRQ. Sorry, moving on, next page. Sensory adaptation has come up on free response recently. This was the nose blind example. Once you're exposed to a certain, scent for a period of time, your senses are going to stop responding. And so you may not notice that smell where someone else comes into your house and says, oh, your house smells so good. And you're like, I don't really notice the smell. That's because of sensory adaptation. After a period of time, constant exposure to an unchanging stimulus, we stop responding to it. Okay, so with vision, I just want to go through that vision pathway real quick. I'm looking at the picture of the eye. The cornea, the outside covering, protects the eye, helps kind of bend and shape light as it goes in through your pupil. Remember, the iris, the colored part of your eye, is a muscle. It controls the size of your pupil. So the more light you're exposed to, the more that iris is going to constrict that pupil. When it gets darker or it's more dim, that iris is then going to dilate and make the pupil larger. The pupil is just a hole. It allows the light to go in through the eye. Once it passes through the pupil, the first thing it hits is the lens. So the lens, remember that clear disc behind the pupil, that is where accommodation occurs. Accommodation is the process bending and shaping light onto the retina. This is the part of the eye that helps us with our near side and far side vision. When I'm focusing on something that's up close, the lens adjusts the light accordingly to the retina. If I want to focus on something far away, same thing. What happens as we age, that lens gets harder. It's not as flexible, which is why your parents need reading glasses. When people get older, they can't see up close as well because of the lens aging and getting harder. Moving on from the lens, like I said, it goes back to the retina. Now remember, what's really, really important, you can flip to the next page. The retina is where transduction occurs. Okay, transduction is that transforming your stimulus energy, in this case a light wave, into a neural message. So this happens here with those sensory receptors that are called rods and cones. Okay, the rods and cones, I want to focus on those for a second because they have come up on the AP exams, FRQs. The rods, remember, we have more of. We have lots of rods compared to cones. And so the rods are used for our night vision, dim, poorly lit conditions, black, white, grays. That activates the rods in our eyes, but they line the periphery of our retina. So when we are looking in our peripheral vision, our rods are activated, which is why we can't see a lot of detail out of our peripheral vision. It's why we can't see as well when it's dark or at night. Okay, when we want to see things well, we turn lights on. The rods are activated in dim light. They are not used to see detail. Okay, fine detail is detected by our cones. So the cones are what allow us to see in color. We all know, and we'll talk about this in a second, but we have cones for 3 colors. Those cones are what allow us to see all the color that we see. They are activated by brightly lit situations. There are far fewer cones, and it's also important to know, because this was on the AP exam in 2016, is the fovea. They actually worded it, they made the term on the FRQ foveal vision, but remember that your fovea is the center of the retina where the cones are clustered. So your cones, for your most detailed color vision, they're clustered there in the center of the retina in the fovea, and that is your most acute, most detailed vision. So from the rods and cones, that's where transduction occurs. So when that light reaches, and I don't know, I guess I could hold this up. So when that light reaches the retina here, this layer has three levels. The very back is your rods and cones. That's not helping at all. I don't know why I'm holding that up. It's not helping. Sorry. So the very back of the retina is where the rods and cones are. Once the light hits the rods and cones, now that light is turned into a neural message. It can now be passed on through our nervous system to the brain. So from the rods and cones, it goes through the bipolar cells. The bipolar cells send that message on through what are called ganglion cells, which all converge to form our optic nerve. The optic nerve is what carries that message to the eye. Okay, once it carries that message from the eye to the brain. So once the optic nerve carries the message to the brain, it's going to take it to the thalamus. Going back to a review from chapter 3, remember the thalamus is your sensory switchboard. All of your sensory information is routed through the thalamus except for smell. So once it gets to the thalamus, it will then take that visual information and direct it to the occipital lobe. Okay, where your visual cortex is, and that's where the feature detectors are. Feature detectors have also been on recent FRQs. Remember, very important, if you don't have this written down, please write it down. Feature detectors are in the brain. They are not in your eye. They are in the brain, in that visual cortex of the occipital lobe. That is where that perception starts. That's where we start breaking down all of the details of what it is we're looking at. Okay, so lines, angles, shape, color, depth, form, all of those things start getting put together and communicating with the different areas of the brain for our visual perception. Okay, so moving on to the color theory. So going back to what I mentioned before, we have 3 color cones in the eye. So that's that has been presented to us in the trichromatic color theory. Trichromatic color theory just basically says, our ability to see in color is dependent upon activating those receptors in the eye. We have receptors for red, for green, and for blue. Okay, and I actually came across this acronym. You all know what Roy G. Biv is, right? How you know the colors of the rainbow in order. So if you think of Roy G. Biv's initials, RGB, red, green, blue. Those are your 3 color receptors in the retina. Okay, so that's your trichromatic color theory. If you have a deficiency, so if you are colorblind, most people who are colorblind are what is called dichromatic. That means instead of having 3 functioning receptors, they only have 2. We got to see that demonstrated when Mr. Freed came over and did the colorblind test in our classroom. If you are monochromatic, meaning you only have 1 functioning receptor, you probably have very, very poor vision. Most people who are monochromatic, they're like legally blind. They usually cannot see very well in detail at all. They're limited to like shadows, shapes, figures, but not real detailed vision. It's probably not going to be important for the exam, but so just make sure you know that. And then the opponent process theory. So the opponent process theory, this is the theory about our perception of color. So when we start talking about how we perceive, what this theory says is that we basically, our perception of color is affected by these 3 opponent systems. Okay, so basically that's the red-green opponent colors, the blue-yellow opponent colors, and the black-white opponents. So what they say is when we activate one of those, we are inhibiting the other. So we don't see a cross of red-green, a cross of blue-yellow, a cross of black-white. Okay, I don't know. I know we talked about that. They demonstrate this with the after images. You stare at, the flag. We looked at a American flag that was yellow, green, and black. And we looked at that. And then when we flash to the white screen, the idea is you're exhausting those color receptors so you see their opponent colors. It activates their opponent colors, causing you to see the red, white, and blue flag. So moving on to the next page, we'll go into hearing. Some of the things that they have focused on, one is just making sure you know kind of the pathway of a sound wave. So we just went through the pathway of the light wave. The sound wave is pretty simple. I have the picture of the ear there for you, outer, middle, and inner ear. It's vibrations. From the auditory canal, we vibrate the eardrum, which then vibrates the 3 bones in the middle ear, hammer, anvil, stirrup. And then it goes to the inner ear. And this is where the important stuff happens, kind of like the retina in the eye. This is where we vibrate that oval window. My lights just went off. Hold on, I need them to come back on. Okay. Sorry, I have to go activate the little sensor. Okay, sorry. So anyways, so the stirrup is attached to that oval window. That's the base of the cochlea. When that vibrates, that's when the fluid inside the cochlea starts to move, activating the hair cells. Now, oddly enough, the term basilar membrane also came up in 2016, was on an AP exam once, on an FRQ. Most of you are probably like, well, what is the basilar membrane? I didn't even put it on your, I didn't even put it on here, so I apologize. The basilar membrane, B-A-S-I-L-A-R membrane, that is that lining of the cochlea. It's just the tissue that lines the inside of the cochlea that contains the hair cells. I hope that they would not put that on another FRQ because people are not very happy about it because it seems like a very insignificant term. But just so you've heard it, it is in the cochlea. That's where your hair cells are. Your hair cells, remember, are your sensory receptors for hearing. That is where transduction occurs. So once we activate those hair cells, now that sound wave is transformed into a neural message, gets carried to the brain via the auditory nerve. The auditory nerve will take it to the thalamus. The thalamus will then send it to your auditory cortex, which remember is in the temporal lobe. So, so there's the ear, cochlea, hair cells, basilar membrane, the big stuff like in the retina with the retina, retina, rods, cones. Those are things I would focus on if you're looking at the ear and the eye and what to study. Making sure you know where that actual transduction happens will be important. Okay, moving on. Just because I'm skipping stuff doesn't mean you don't need to know it. I just, like I said, I don't want to be on here for an hour. So I do want to make sure that you focus on knowing the difference in kinesthetic and vestibular sense. So remember, kinesthesis, this is all throughout the body. These are sensors that are in all of my joints, my muscles, my bones. And what they do basically is when I move my arms, my legs, those sensors are sending messages to the brain, to the sensory cortex. Remember, the sensory cortex is what allows us to detect our body positioning, not just our tactile sense of touch, but also our body's position, so the location of my limbs. That's kinesthesis. Kinesthesis is like the location of body parts. It is your, balance. Obviously, to be balanced and equal, you need to know where your arms and legs are located. But it's those sensors throughout the body that send messages to that sensory cortex in the parietal lobe to allow us to be aware of the location of our body parts. So if my arm is raised, if I am sitting, standing, laying down, in a handstand, etc. Where the vestibular sense, remember, that's the one that's linked to the inner ear. It's those semicircular canals that are there, and I will use the picture here. So they're right here, right in here with the cochlea. I know this picture's not very clear, but you have it right there in front of you, and they're labeled for you. So the semicircular canals are also in the inner ear, but remember, have nothing to do with hearing. That is your vestibular sense. So the movement of the fluid and crystals in those, they're called vestibular sacs inside of those tubes. That is what affects our equilibrium, our sense of balance based on our head positioning. So when we spin around in a circle real fast, or we do, we stand on our head and we come up, we can feel kind of like that sense of being like a little dizzy or uneasy. That is because of the movement in those canals that, kind of throws off our balance or our equilibrium. So those two kind of work hand in hand, but make sure you know the difference, and make sure you understand the semicircular canals, and their role is not in hearing, but is in that vestibular sense. Okay. The only thing I'll say about taste and smell, I didn't even put taste on there, is just their chemical senses. So they're activated by chemicals from our environment, either, particles in the air, odor particles that we either take in through the nostrils, or chemicals that are in things that we eat. So, and I also put that chart in there. This chart, it's out of your textbook, but it's a good reference to have just so you guys can kind of use that for a last minute if you need to look over anything. All right, I want to move on to perception, because they've actually put a good amount of perception on the FRQs in recent years. So starting with Gestalt. Know what Gestalt is. Gestalt is just that idea that we organize information, especially visual information, into meaningful wholes. Instead of looking at things in each individual piece and part, we group things and we look at them as a meaningful whole. Our brain likes to organize and make sense of things. So we talk about figure ground here, pulling a figure from its background. And I'll go through that chart, the table on the next page in a second, and what the right answers are to that. But know what figure ground is. Know your grouping principles. So we group things based on things like proximity, meaning their closeness to one another. Proximity has been on the AP exam recently. Figure ground has been on the AP exam recently, as well as closure. Closure is that grouping principle that we kind of like to fill in the gaps, fill in any missing pieces or information that's not there, like the picture I showed you of the panda bear, the giraffe. We had some different ones we looked at in class, but that's closure. So those are some of your Gestalt principles. Just be familiar with those. Moving on to binocular cues. So the only one, and it has been on the AP exam twice in recent years, that you want to know is retinal disparity. We know what the retinas are. We know disparity means difference. That's exactly what retinal disparity is. It's a binocular cue, which means requires the use of both eyes too. But it's the difference in the image that is being viewed on each retina, because our eyes are, slightly set apart on our face. And so as an object moves towards us, so if I'm playing ball, I'm playing catch, I have a glove and someone's throwing a softball with me, As that ball moves closer to me, the closer the object gets, the greater the retinal disparity. What that means is, as it moves towards me, the greater the difference I can detect on the retinas of my eyes. When objects are further away, there's little to no retinal disparity. Okay, so retinal disparity, this binocular cue, is most useful as objects are moving toward us, giving us a better judge of their depth and distance. Okay, I hope all that makes sense. But just if it doesn't, please ask. Please send me an email. Please request a Google Meet. I'd be happy to sit down and talk with any of you about this. But that's what retinal disparity is. It's that binocular cue that gives us a better judge of depth and distance, because we are using both retinas to judge the difference of the images coming toward us. So it's much easier to catch a ball when we have both the use of both eyes. It's much easier to drive a car when you have the use of both eyes. Okay. Monocular cues, I'll just touch on those real quick. That's going to be where we only need one eye. With one eye, we can see most of those 2D qualities that allow us to judge depth and distance. And so with that, on the next page, we see some of those perceptual concepts, and there are images, and then you were supposed to just identify the concept. So the grouping principles from Gestalt were here, and then the some of the monocular cues were here, and then some of the perceptual constancies. So let me go through those. I'll start on the left side, and I'll just go straight down the left side, each one of those images, and then I'll move to the right column. So on the left, the first one is proximity. So you're looking at the rows of just dots and how we group them based on their closeness to one another, or their proximity. Then it's similarity. Just grouping the shapes based on their likeness or their similarity. The next one is continuity. So as we look at, I guess it's probably a logo for a business, but it's an H, but we see it's broken up, but our brain puts together continuous lines, and that continuous kind of swoop through the middle so that we see an H, something that we can organize and make sense of. The one below that, using that Rubik's Cube, it's hard to tell if it's in black and white, but like with the shadows, that is that color or lightness, brightness constancy. So we use that example in class. We even looked at some examples through videos, but all that color constancy means is that colors are perceived to be the same, even though the light that they're reflecting is changing. Okay. Under that is texture gradient. We didn't talk about that in class. That's okay. Most of you got it right. Texture gradient is just when we're looking at images and being able to see details in texture. It helps us to judge depth and distance. The next one with the circle and the square is just interposition. You have one object overlapping the other, allowing us to judge the depth of the square being further away than the circle. And then the bottom one is light and shadow. So you can see the way they've used the shadowing there to show depth and distance. Going to the top of the right-hand side, the first one is closure with the overlapping triangles. We close in, make a complete triangle instead of fragmented pieces. Same thing with the circles. The one below it, I did actually use in class the tree with the lion, and the gorilla is figure ground, so pulling the figure from its background. Then it's size constancy. So looking at the cars there, even though the retinal image that the cars cast is different, we know that they remain the same size because we know they're relatively all the same. So our brain doesn't perceive one as being smaller or larger than the others. And then the one below that is shape constancy. So same thing, shape remaining constant even where the retinal image changes. Below that, the converging lines is linear perspective. Then we have relative size. So the example in your book was the little man with asking the woman if she had a police officer in her hair, or he said he had no depth perception. Is there a police officer on the corner? Is there a tiny man in your hair? It was something cheesy like that, but it's in your textbook. But that's just that relative size. And this is kind of one of those fun pictures where people use, it looks like, because the hands and the person It makes it look like the hands are really big and the person is very small, where really the person is just very far away and the hands are close. You guys get it. Anyway, so that's relative size. And then the last one is phi phenomenon. So the like random and quick blinking succession of lights to give us the perception of movement or motion. Okay, so that wraps that up. I only got on with a few people last night. I'm only getting about 10 to like 12 of you get on Sundays. If Sundays don't work for you and you would like to have a Google Meet, like get with a group of people, send me an invite. Let me know. I am happy to meet with you guys and do a Google Meet anytime. It doesn't have to be Sundays. I was just trying to come up with a time that wouldn't interfere with your other classes. And I want to keep them optional, but I also want to stress how important it is, especially as we get closer to the AP exam, for you guys to really start narrowing down and asking those questions you have before it's time to take the exam. So think about that. Talk to some of your friends. If you guys have got questions or anything you want to discuss with me, let me know. Shoot me an email and just say, hey, would you be able to jump on and do a meeting with us at this time? And probably 90% of the time I'm going to be able to. I'm not super busy. I don't have a ton going on other than trying to prepare you guys. So let me know. Happy to meet with you guys. I'd love to see your faces. And if nothing else, just catch up and say hi and see how you're doing. So like always, I miss you guys so, so much. And I wish more than anything that you were sitting here in these desks and I wasn't just talking to myself. But, it is what it is. We'll get through it. But please use me as a resource. Please reach out and let me know if there's anything that I can do to help you guys out. I'm more than happy. Okay. So good talking with you. And I hope to hear from you soon. Bye guys.